Okay, so this video is going to be on volumetric analysis. Essentially, it's going to act as something where I can introduce you to the vocabulary and the idea of what we're going to do, but this we will mostly do through experiment. There's no way better than to learn this than by actually doing it in class, which we'll do over a couple of lessons. Essentially, a volumetric analysis is looking at chemical reactions between substances in solution. So we're always looking at things that are dissolved, aqueous. We're not looking at precipitation reactions. They're always aqueous solutions. And we use it to determine how much of an unknown substance there is by reacting it with a solution of known substance and known concentration. So we might have say a bathroom cleaner that has a base as the active ingredient in it, but we don't know the concentration of that base. So we would react it with a solution of acid that we know the concentration of. And then however much acid it took, we can work out how many moles of equivalent base would be there. So we use this essentially as an analytical technique to figure out something that we may not know. We often use this for vitamin C titrations as a common IA, where you want to work out the vitamin C concentration in food, and you would grind up the food and make up a solution and then do a titration to figure out the vitamin C concentration. There's a lot of things that we can use this for, so it's a technique that we will definitely look at in quite a lot of detail. We tend to use this as a fast and convenient technique. A lot of the equipment that we use doesn't require a lot of money or specialist training to be able to use effectively. So you can get very accurate results even if you're a high school student. Okay, you don't need years and years of training to be able to do this technique well. It's an alternative to what we call gravimetric analysis, which would be where we perhaps precipitate out something that was in a sample and then measure it by precipitation. Doing that requires us to first be able to find something we can adequately precipitate, and then we've got to collect the precipitate and dry it, and can take a lot longer than what this solution technique can do. What we have here is essentially the equipment that we see used in gravimetric analysis, and that is our beaker, conical flasks, measuring cylinders, volumetric cylinders, pipettes and burettes. It's these last three that will be quite new to you in terms of equipment that we haven't used much in class. Our beakers we largely just use to hold solutions. They're not very accurate. Our conical flasks is what we will titrate into. Volumetric flasks we don't tend to use very much because their uncertainty is too high. These measuring cylinders, but the volumetric flask allows us to make a very accurate solution, and the pipette allows us to transfer a very accurate volume as well. The burette allows us to deliver a varied volume quite accurately. So one of the main things that we need to do in order to carry out a volumetric analysis is have a solution that we accurately know the concentration of. Now this is generally referred to as our standard solution, and it will be made out of a chemical that we refer to as our primary standard. Primary standard is something that is nice and stable, can be stored, is cheap and easy to get a hold of, and won't react with the atmosphere or things like that, which means that we can store it long enough to do our analysis, and we can weigh out enough to really accurately know our concentration. How we usually do that is we take a beaker or a weighing boat, we weigh out an accurately known mass of the solute, and then we dissolve it up into our volumetric flask, otherwise known as a standard flask. We half fill it, give it a good shake to dissolve everything, and then we fill it so that the bottom of the meniscus sits on what we call the calibration mark. And you will be doing one of these in our next lesson, preparing your standard solution. So there are essentially a lot of terms that we need to know for volumetric analysis, and it takes a little while to get used to them. The burette is the long glass tube, and it delivers a variable volume, and it does so very accurately. We can estimate it to 2 decimal places, and it has a really small uncertainty, so it allows us to deliver accurate volumes. The pipette, this isn't like the squidgy plastic pipettes that we've used before. This is a volumetric pipette that is glass and only delivers one volume. We get them in different sizes, so they can be 5 ml, 10 ml. The one we most commonly use for volumetric analysis and titrations is 20 and 25 ml, or 25 centimeters cubed, and that is a very precise piece of glassware. Titration is the name that we give to the technique in which we do the analysis, and essentially it's any analytical technique where we use a burette to deliver a volume. The equivalence point, we talked about that when we talked about indicators, is the point where the titration, where the reactants have been added in stoichiometric proportions. So that is in a 1:1 ratio or 1:2 ratio based on the equation. The end point, however, is the point at which the indicator changes color. So that is usually about 1 drop after our equivalence point. The indicator, we talked about these, are a weak acid and conjugate, where the weak acid is a different color to the conjugate base. So it's a molecule that has a different color in its protonated and deprotonated forms. Aliquot, which sounds like a pretty strange term, is actually what we refer to as any volume that is delivered by a pipette. So if we deliver a 25 centimeter cubed volume into a conical flask from a pipette, that will be referred to as the aliquot in our analysis. So it helps when you're doing questions to be able to figure out which bit is going into what piece of glassware, and the terminology that they use can help us be able to do that. The titer, the T-I-T-R-E, which is titer, is the volume that is delivered by the burette. So any volume that is said the titer volume was 18 centimeters cubed, we know that volume was delivered from the burette and then can trace that back to whatever solution we had filled the burette with. One of the particular things that we need to do with a titration is actually make sure that we have concordant titers. Now, concordance basically means in agreement, and we will repeat a titration until we have a minimum of 3 concordant titers. Now, depending on the textbook, they change what concordance is considered. Most will say 0.05 centimeters cubed, which is quite a small volume, about 1 drop, but the IB and even VCAR for VCE accept a concordance of plus or minus 0.1 milliliter or centimeter cubed in range from the highest to the lowest values. And then we would only use those ones that are concordant to average out our results and work out our analysis from. So when we do a volumetric analysis for an acid-base reaction, we will make up our standard solution. It's quite often an alkali solution, but it's not always. We will pipette out 25 centimeters cubed of that into a conical flask and add the indicator that has been selected for the right endpoint in our reaction. We'll place the acid in the burette and then read the starting value. It is not always the acid in the burette and the base in the conical flask. Sometimes in some analyses we will put the base into the burette. So don't always count on it being the same chemical in the burette each time. Always read your question carefully to figure out which chemical is where. Then what we do is once we've recorded our initial value, we'll run that solution down and record the value once the indicator has changed color. Then we repeat that to see if we can get concordant values. So this is a diagram that goes through the process. So essentially we fill our burette with, it could be our acid or our base. We take the aliquot delivered through the pipette and then use that to deliver this volume, which will be our aliquot, into our conical flask. Once we've got the aliquot in the conical flask, we add the indicator, which will make it go one particular color. We take our initial reading and then we run this solution down drop by drop while swirling the flask into our conical flask. So in here will be an acid-base neutralization reaction occurring. So we have an acid-base neutralization reaction, and then from that, as soon as we see it change color, we will know that we've reached our endpoint. And how accurately we can determine that color change can influence how accurately our titration works. So this is another way of looking at it. We have an unknown sample that we then may want to, if it's a solid, we'll weigh it out, dissolve that into our conical flask, take an aliquot of that mixture, titrate against that, and then from that we can use the concentration and the volume of our known solution to work out the number of mole that was delivered from the burette into the flask. If we know the equation, so say we're doing a HCl plus sodium carbonate, okay, which is going to give us CO2 plus H2O and NaCl, and it'll be 2. We're going to have a 2:1 ratio here. So if I deliver the equivalent of 0.05 mole of HCl into this flask to reach my endpoint, because it's a 2:1 ratio, I know that I must have had half the number of sodium carbonate in my flask. And because I can work that out from my equation, I can take this known solution and use that to work out the number of mole of my unknown, and then back to work out the number of mole in my sample. Therefore, being able to figure out the overall concentration in the original sample, which is what I didn't know. All of this is a matter of technique, using the equipment properly, practicing using a pipette and filling it. This is a pipette here, and making sure that when we read the meniscus, the very bottom of that curve is what's sitting on our calibration line. Okay, we will have some practice using this equipment. Essentially, we want to make sure that we are operating the equipment properly and can fill it and are comfortable with it before we do our analysis. Reading the burette, when you read a burette, okay, you give the titer to 2 decimal places. Now, so if we were to look at this one, we can see here we've got 19 and it goes to 20, so it's going up. So this would be 19.5, 19.4, this is 19.3. It's just a bit below 19.35, halfway between these two. So we could say that our estimate is 19.38 or 19.39 milliliters or centimeters cubed. So making sure that we estimate that second decimal place as accurately as possible helps us get a more accurate analysis. So what I might do is stop this here, and we will look at these examples once we are more familiar with the equipment.